Right, welcome everyone. So it's another edition of the Symmetry in Newcastle. Our first speaker of today is Libor Barto from Charles University in Prague. It's a great pleasure for me to have him here because he's actually from my alma mater and he taught me in my first year of undergrad. So that's very special. And his talk is Constraint Satisfaction Problems and Symmetries.
You are still muted, Libor.
Hello, everyone. Yeah, I have some message here. This meeting is being recorded, and I cannot get rid of it. Okay, let me try.
It's
still there.
You are seeing that because you are a co-host.
Okay, good. I got rid of it. So yeah, thanks for having me here. You see here that I'm shamelessly reusing slides from some other talk. The reason is that I was looking at people who will be listening to me. So I opened this website of the Symmetry group in Newcastle, and I read there, symmetry is accounted for mathematically through the algebraic concept of a group. And I very much disagree with this. So I use slides for the talk explaining that this is not the case. Okay, group certainly is an object capturing symmetry, but this is quite just limited. Well, it's just one object that captures it. There are many more, and one of them I will talk about. So yeah, let's just move on. All right, so here is a quiz. You look at these shapes, which of them are more symmetric and which of them are less symmetric. Okay, so maybe I should first specify what these drawings should mean. I guess you may know I'm drawing here graphs in this case, or directed graphs. So let me just recall the definitions or what these concepts are. So by a graph here, I mean a set of vertices. These are the dots here, and some set of undirected edges. By a digraph, I mean the same thing. This time the edges are directed, so they have some direction. Like here, it goes from this vertex to this vertex, not the other way around. Here it goes both ways. Okay, and next crucial concept for us will be homomorphism. Again, it's clear, I guess, but let me just recall it briefly. So by a homomorphism, I mean a mapping from vertices of the first graph to the vertices of the second graph that preserves edges. Okay? It doesn't necessarily preserve non-edges, it just preserves edges. So here is an example of a homomorphism. This is digraph A, this is digraph B, and this barely seen arrows should indicate the mapping, and it should be a homomorphism mapping, meaning that if I take an edge like this one and I map it by the mapping, so I get this one and it is an edge. Fine. Okay. Well, yeah. If I'm too fast or whatnot, just feel free to interrupt me. Okay, endomorphism, that's homomorphism from A to A, and automorphism is an invertible mapping from A to A. Okay, and your website thinks that this is the concept of symmetry. Maybe you can be more generous and admit endomorphisms as well, because they also give you symmetry. But okay, now when these terms are, hopefully we are on the same page. Let's look at the pictures again. Which of these pictures are symmetric, right? So the answer you probably have is that this first guy is the most symmetric one. Whatever permutation of the vertices is a homomorphism or an automorphism. So it's perfectly symmetric object. What can be more symmetric than a triangle? Okay. The second one, it's still quite symmetric. We are losing some symmetries, like the mapping that just flips two of the vertices and leave the third one at this position, but we still have this cyclic permutation preserving all the edges. Okay, and the third one, well, it's a mess. Okay, so not symmetric at all, and I guess you expect an unexpected answer. So we will see in a while that the order is the other way around. Okay, so this is the most symmetric object, this is the slightly less symmetric, and this is totally non-symmetric thing. Okay, so that's where we are heading now. Okay, so here is the outline. I'm talking about symmetries in constraint satisfaction problem. So I will introduce that first. Then I will talk about what the CSPs have to do with symmetries. And then I'll tell you very briefly some tools, talk about some tools that are used to analyze the symmetries. Okay. So CSPs, or constraint satisfaction problems. So here is one example, one concrete CSP, and this is the well-known three-coloring problem. What it is, so it is a computational problem. It has some input and it expects some output. The input in this case is a graph, so set of, this is the X here in this picture, set of vertices and some undirected edges. And what we want is to output a homomorphism from this graph to the undirected triangle, if it exists, okay, or say it doesn't exist. So yeah, in this picture, we have some complicated object on the input, and we want to map this to the triangle. So what does homomorphism mean in this case? If we label the vertices of the undirected triangle by, say, red, pink, and black, we want a mapping from vertices of X to this. So we want to effectively color these vertices by one of the three colors. And the condition that it is a homomorphism says that if two vertices in X are adjacent, then their images must be adjacent. And because how this triangle looks like, everything is adjacent, but the pairs of equal colors. So red is not adjacent to red. So meaning we want adjacent vertices to be mapped to different, well, to have different colors, right? So that's why three coloring, we want to color these vertices by one of the three colors. And we want to make it so that adjacent vertices have different colors. Okay, and well, what we ask in computational complexity is how fast can this be solved? Okay, so I guess this is a well-known problem, perhaps also to you. But anyway, I really not quite sure about the background. So here is a course in computational complexity. Let me just go very quickly through this, but stop me if something is not clear. So by a computational problem, we mean some object that we have, where we have specified class of inputs, and we say what we want as an output. Okay? And one example is the three coloring problem on the last slide. We specify that our input is a graph, and what we want is output, which is the three coloring. And there are many other problems, we say that such a computational problem is in the class P, like polynomial time, if it can be solved by an algorithm running in polynomial time with respect to the size of the input. And size here, for example, is the number of vertices for the three coloring problem. We say that the problem is in NP if correct answers, like correct three colorings, can be verified in polynomial time. So the three coloring problem is in NP. And we call a problem NP complete if it is hardest in NP, in a sense. Okay, and of course there is this tedious question whether actually NP is equal to P or not. Okay, so that's somehow what we will need from computational complexity in this lecture. So some examples of computational problems. And in fact, all of them are in this class I'm talking about, in the class of CSPs. So one example, the 5 coloring problem, or 3 coloring, or 4 coloring, or whatnot. Another famous example, the 3 satisfiability problem, where we want to find a satisfying assignment to a propositional formula of this form. So it's a conjunction of clauses, where each clause is a disjunction of 3 literals, and each literal is a variable or a negated variable. So we want to find a mapping from variables to 0 or 1, or true or false, making all these clauses or constraints true. Another example of a computational problem, solving systems of linear equations over Z2, over the 2-element field. The input is a system of linear equations like this one. And what we want is to find a solution in the 2-element field. Okay? So many other problems of the sort, solving equations over whatever. Okay? Linear programming, another example. The input is a system of linear inequalities over Q, and we want to find a solution to them. Okay, so this is a bunch of examples. All of them are CSPs. So let me now tell you what this constraint satisfaction problem is. And I will be actually talking about a very small class of CSP-like problems, which are called fixed template CSPs. So what is this about? We fix a finite, well, for now, let's fix a digraph, perhaps infinite. Let's call it A, so this is fixed. And for each A, we'll have a computational problem, which I'll denote by CSP over A, like this. So what is the input to this problem? A finite digraph X, and as an output, we want to find a homomorphism from X to A, or say that no such homomorphism exists. Okay. So instead of a digraph, we can have some other structure, but let's ignore this. It works the same way. So again, this is a class of computational problems. For each structure or a digraph, we have one computational problem. And for this problem, we ask what is the complexity, say computational complexity. Now, how broad is this framework? Well, quite broad. If you allow any structure that this framework captures all the computation, every computational problem is equivalent, like polynomial time, equivalent to CSP over some fixed structure. Okay, so this is not a like thin framework. It captures everything, all the computation. That's, I guess, why for now we need to limit A to some small class. And what I'm going to talk about here is the class of finite digraphs. Okay, so for finite A's, it is still quite a nice framework because it captures problems like tree coloring, where I present it in this form. The template, the A, the fixed digraph, is the undirected triangle, which we model as a digraph, like this. So all edges go both ways. So if you take A to be this one, CSP over A is the tree coloring problem. Now, if you cook up some other digraphs or structures, you get problems which are exactly 3-SAT, for example, or any other forms of SAT. If you fix A to something else, you get linear equations. See this problem of solving linear equations over the 2-element field, and so on. Okay, so this framework for finite templates, it's way smaller than the general one, but it still captures quite a lot of problems. And one advantage is that such a problem is always in NP, because if you give me a mapping from X to A, it is easy to check whether this mapping preserves edges. Okay? On the other hand, if you allow general structures A, you can get whatever complexity. So, for example, you can get undecidable problem. Right? If you take, say, Z with some relations capturing Diophantine equations, you get undecidable problem. Okay, so this is the CSP over A, and this is what I'm talking about here. Of course, there are like many variants. What you can do, you can still have finite domains, which is some of the most popular special case, and ask different questions like how many homomorphisms are there, or maybe there is no homomorphism, so you want to optimize the number of edges or which are preserved, or you want to approximate, and many others. Right? Any questions so far?
So far, so good, I believe.
Very good. Cool. So now, what does it have to do with symmetries? So what is a symmetry in here now? A symmetry is a polymorphism, not an endomorphism, but a polymorphism, and it is a straightforward generalization if you allow multivariable functions instead of unary ones. Okay, so here is some definition. Say we have a digraph, so set of vertices V and set of edges E, which is a subset of V squared. Now a mapping from V to the N, so this is the reference, we have some N here, V to the N to V, is a polymorphism of A if it preserves edges, meaning if you take M edges like this, V1 to V1 prime and V2 to V2 prime, and so on, and you apply F to the edges coordinate-wise. Okay, so you apply F to the like source vertices, and you apply F to the target vertices. What you get is an edge again. Okay, so it is exactly like an endomorphism, but endomorphism would have just one argument. Now we are allowed to have many arguments. Nothing spectacular, and it is still some kind of symmetry, okay, but it's maybe better hidden. It combines more, more vertices into one. So you don't see it directly if you draw. If I draw you a digraph, you won't see directly what the symmetries are, okay, what the polymorphisms are. But nevertheless, these are important symmetries in this context, as we will see. But first, perhaps some examples. So if you look at the directed triangle A, so one polymorphism is this unary endomorphism rotating vertices. That's still a polymorphism, but a kind of boring one, just unary. It's even an automorphism. But there is a less obvious symmetry, like this binary one. If you consider this mapping that sends xy to the initial vertex of an edge. Okay, so if x has an arrow to y, x times y, or fxy would be x, and fyx would be x. I haven't defined it for xx actually here. So fxx is x, okay, by definition. Okay, and then, well, easy check, but it's not just completely obvious from the picture that this is a polymorphism. So for example, if you take the edge 0, 1, and then you take the edge 2, 0, and you apply f to the sources, you get 2, and then f to the target vertices, you get 0, and you see 2 has an edge to 0. Okay, and if you check all the, I don't know how many possibilities, it all works, hopefully. Okay, so this is a less obvious symmetry as well, this f. And for this context, the CSP over A, this symmetry is more important than the obvious one, the rotation. Okay. Another example from real life, say if you take this digraph, it's maybe weird to look at it as a digraph, but anyway, so the vertices are the real numbers and the binary relation is some convex subset. Okay, this is not very convex, so convex subset of R square. Then we have these important symmetries, which are convex combinations. So for example, this binary function sending xy to 0.3x plus 0.7y. This is a symmetry. If you take two elements of R square, which are now edges, which is a bit weird, apply f to these edges, what you get is the convex combination of these 2 points x and y. Okay, and by definition of convexity, the point is there as well. Okay, so you can say that a shape or subset of R squared, say, is convex if all these binary functions of this sort are polymorphisms. Okay, if it has enough symmetries. Okay, so this is a polymorphism, and why I talk about them is that they capture the complexity of CSP. Okay? So an observation by Jevons is that if you take all polymorphisms of some digraph A and it contains the set of polymorphism of another digraph B, so say B and A have the same vertex set, otherwise it doesn't make sense. Okay, so A and B have the same vertex set, and each symmetry of B is also a symmetry of A. Okay, so A is more symmetric, and because it's more symmetric, it's computationally easier. Okay, so in this case, CSP over A is no harder than CSP over B. So if we allow not only unary boring group like symmetries, we now have this this fun fact that complexity depends only on symmetries, and then you can say that the more symmetrical object is, the easier it has the easier CSP over this object is. Okay. Okay, so there are some improvements, and I guess I'll get to one of them, which says that, well, now the question is, we know that these polymorphisms capture complexity. The question is, what kind of information I need to know about these polymorphisms? Okay, do I need to know a complete list of polymorphisms or just some information about it? and this is what this follow-up work is about. But overall, okay, so the long-term goal is really to be able to say that complexity depends on symmetry for all computational problems. That's somehow the long-term goal. I told you that CSPs capture all computational problems actually, but what I write here works for finite domains. Okay, it works also for some infinite ones, not all. But anyway, it would be fantastic to have such a thing because somehow I feel this could be this should be the approach to the basic questions in complexity. Okay, like PNP or whatnot. We need to find the right notion of symmetry in computational problems. But we have this one for CSPs, that's for sure. Okay. So let's see. So here is just comparison between maybe usual symmetries like endo or automorphisms and polymorphisms. Okay, so what it is? Well, endomorphism is homomorphism from A to A. Here the only difference is that I allow multiple inputs. We always have some notion of a trivial symmetry. For unary things, we have the identity, which is always symmetry. Here we have what some community calls dictators. Okay, so these are the n-variable functions, which the only thing they do is they return the ith input. Okay, so if it's a voting system, the ith guy always wins. That's why dictators. Now, if you collect all symmetries of an object, if you consider only unary ones, you get transformation monoid. Or if you just really very strict and consider only bijective ones, you get permutation group. Here, the object is called a clone. Okay? So it's a clone. And like, what are the where is it studied? Well, we have semi-group theory for the unary, boring ones, and then we have universal algebra for the real ones. Okay. Okay, and here is one of the one answer to what exactly we need to know about the symmetries, about the polymorphisms. It turns out that CSP over A is equivalent to this problem. The problem is about solving functional equations. So the input is what I call trivial, I'll get to it, trivial system of functional equations. Functional equation is something of the form, well, they're very special, they're only on this form. So function symbol variables equal to function symbol variables. Okay, so here is an example, maybe best to look at an example. This might be an input to this problem. Why I call it functional equation is because we are not looking for, so these m's are, or f's of the functions, these are not fixed functions. So we are not looking for evaluation of variables, making these equalities true. Rather, we are looking for these functions, m, f, g, which make these equations true universally. Okay, so we want for each x, y, z, for each x, y, for each x, y here. Okay, so it's not equation for variables, but for functions. Okay, so the input should be a trivial system. What does it mean to be a trivial? Trivial means solvable by dictators, by this most boring symmetries that only return some fixed variable. Okay, let's see. So, is this system trivial? Is it solvable by equation, by dictators? Well, I hope so. So maybe let's try. So maybe M would be the first dictator. Okay, so M of A, B, C, D. Let's try this. Is A. Okay, so the left-hand side here is always X. So I guess I want this F to be the third dictator. Okay. And then the first equation is true. Then I want G to be the first dictator, it seems. So GAB is A. And then this equation is true. And if I correct, then the third one also works. Okay, so this this system of functional equations is solvable by dictators. It's trivial. Whenever I have dictators, I can solve it. Okay, so now back what I'm actually talking about. So the input to my problem is a trivial system of functional equations. And what I want to do is to solve it, but I'm allowed not only to use dictators, but I can use any polymorphisms of A, any symmetries. Okay, it turns out that this problem, which is solely about equational solving, is the same as the CSP problem. So if the only symmetries, only polymorphisms are dictators, then this problem is just, I get a trivial system. I want to know the dictators solving them. If I have more polymorphisms, then perhaps I can solve it more efficiently. Okay. And here you see that what kind of information I need to know about polymorphisms. I don't care what the concrete functions are. I somehow just care about what functional equations they solve. So far, so good. Okay, so let's think about it for a while, what it tells us about CSP. So here is just to recall the theorem that CSP over A is the same as solving trivial systems of functional equations by polymorphisms, by the symmetries. Okay, so we see that the more special equations, the equations of the form F variables is equal to G variables, the more special equations polymorphism satisfy, the easier CSP is. Okay, if we satisfy only trivial equations, only those ones which are satisfiable by dictators, then the problem must be the hardest possible, therefore NP complete. And okay, if we have strong enough equation, then it should be NP. At this moment, we don't know where the borderline is, but we know that the complexity depends only on functional equations, the special ones satisfied by polymorphisms. Okay, so this is the second thing. Complexity of the CSP only depends on equations satisfied by polymorphisms. And this kind of abstraction, instead of considering concrete functions, we consider only equations among them. It's very similar to the abstraction from a permutation group to a group. Okay, so if you have a permutation group that's a family of mappings, and then you can forget what the concrete mappings are, you just remember how they compose, right? You have mapping F, and you are just interested of what F composed by G is, and then you call this a group operation. Okay? Here it is similar. If you have a concrete clone of n-ary functions, we can abstract and only care about how the functions compose, or this is somehow the same, saying we care only about equations among its members. And this is somehow what universal algebra is mostly studying. Just like in group theory, you rather study groups rather than permutation groups now, maybe, perhaps. Often, at least. Okay, so maybe it's time to go. Okay, not time yet. So here is just brief history of CSPs. over finite structures. So a very ancient history. 78, Schiffer, he classified the complexity for two-element structures. Then it was classified for these undirected graphs. And then the medieval history starts this influential paper, which speculated that there are only two complexities among these problems, namely P and NP complete. That's not automatic because if P is not equal to NP, there are many problems in between, many classes in between. But well, yeah, the conjecture said this is this is not the case for CSPs, and also already there was some intuition that the complexity may depend on some closure properties, they call it, of constraints. So basically they anticipated that that symmetries govern the complexity here. And then there was some development that it's indeed the case. Then perhaps the next two big steps, one result characterized when we can describe all homomorphisms in a way, so find all solutions, not just listed but find. Second thing, when we can use some obvious local propagation algorithms, this Sudoku kind of reasoning. If this vertex goes there, then this other vertex must go somewhere else, and when you can apply such algorithm to solve it. And then happy end is like 3 years ago roughly, which confirmed the conjecture that there is a dichotomy, and the dichotomy is beautiful. Okay, so as follows from the theorem I gave you, if only trivial equations are satisfied by polymorphisms, then we must be NP complete. This theorem here, this dichotomy theorem, tells us if you have any non-trivial symmetry in this sense, then you are polynomial time solvable. Okay, so it cannot be nicer. I mean, you can some symmetry easy, no symmetry hard. Okay, you just need to know exactly what kind of information about symmetries you need. Okay, and that's not where this story ends. I mean, now we are working in many other variants, and well, somehow towards the overall goal, to push it to the whole complexity ideally. Okay, so now it's time for the right answers, right? So what about our triangle? So every permutation is a symmetry, is a polymorphism, but these are the only ones. Okay, so there are no genuinely binary functions that would preserve this object. So polymorphism clone is very, very poor. Okay, only unary members, and it satisfies only trivial equations. Because groups satisfy only trivial equations. So groups in this context are the trivial objects. You cannot have any interesting equation in one variable. It's always satisfiable by identity. Okay. Now the second one, well, it has less unary symmetries, but it has an interesting one. For example, this one I gave you, it's a commutative operation. Okay, and it is non-trivial because you cannot satisfy this functional equation by a dictator, right? The first dictator doesn't satisfy it because x is not equal to y, and the second one neither. The third one, it has the most beautiful symmetry in this context. It has a ternary function, which is like a majority function. So this equation is satisfied. It is totally like commutative, so to say. Well, this actually stems from the fact that this graph is bipartite, so it has the same symmetries in this sense as an undirected edge. Okay, an undirected edge has this non-interesting for us symmetry which flips the vertices, but also many interesting ones like this one. Okay, so 3 is the most symmetric object. Definitely. All right, so I've just, I guess, few minutes. So let me just just tell you very briefly what kind of math is behind analysis of symmetries, and a lot of math. So the first example is the universal algebra. So this is one result, which is kind of algebraic in the methods used in the proof. So you see, we have this dichotomy theorem, and these guys, Bulatov and Zhuk, needed to prove that if you have a non-trivial system of functional equations satisfied by polymorphisms, then the problem is in polynomial time. Okay, the knowledge of having some non-trivial system is, it's not particularly useful. So people are looking at some, stronger forms of this. So like what concretely, like what the system could be. And it turns out that if you have any non-trivial system, then actually this system of one equation with p variables is always satisfied. Okay, so if you have some non-trivial symmetry, in this sense, you have always this cyclic symmetry. A p-ary function, where p is some prime, bigger than this domain, which is cyclically symmetric. Okay, so symmetrical symmetry, one may say. And the math behind is, so the tool is a theory which evolves around a new concept of absorbing subset. Here it's a very simple concept. Here is actually a definition. So we call a subset of some A absorbing if there is some function from this, which is allowed a symmetry, which does this. So if you apply the function to many elements from B with possible one exception, you still get an element from B. There is a theory around this concept. This is kind of a generalization of the concept of ideal in ring, right? And this generalization to like general algebras turns out to be useful. That's, I guess, all I can say. But well, yeah, there is a generalization of an ideal. It is useful for general algebraic objects, not just very specific ones based on groups. Okay. Another sample here. If you start to approximate or optimize, the field is full of probability analysis and such things. So here is a sample theorem. It's not a CSP as I define it. It's a different version. It's close to 3-sat. So input is in the 3-sat problem, conjunction of clauses. We are promised that it is satisfiable. And what we want is to find an assignment that satisfies a bit more than 7/8 of the clauses. Okay. Now, if you think about it, if you just randomly flip a coin for each variable and assign it 0 or 1, a probability that one clause is satisfied is usually 7/8, right? If the variables are different, but let's ignore this issue. Okay, so the probability with random choice of variables is 7/8 that you satisfy one of the clauses. So expected number of satisfied clauses will be 7/8. Okay, so the random algorithm, just not looking at the instance, randomly picking values, will achieve this. So this fantastic theorem tells us that if you want to achieve anything better than random algorithm, you are still NP-complete. Okay. So the mathematics to prove this is, again, we want to analyze functions, in this case, Boolean functions. And the basic tool here so far is Fourier analysis. The idea is to express this function in a different basis. Okay, so the basis would be the dictators, and then sums of dictators, and then sums of 3 dictators, and so on. And you express it, and then somehow look at the coefficients in this in this expansion, Fourier expansion, and decide accordingly. Okay, so somehow, yeah, if you want to prove something is NP complete, you want to show in a way that functions are close to dictators. So you want to somehow pick important coordinates here, and the way you pick important coordinates for this problem is you look at the coefficients in Fourier expansions. Okay, and maybe one more illustration, like just what kind of math is there behind. This is a topological example. If you want to, so three coloring is NP complete, and this is a sharper result that even if we are promised that the input graph has a homomorphism to some odd cycle, fixed odd cycle, like what is this, 7 cycle, we are promised that it's still hard to find three coloring. Okay, so it's harder to have a homomorphism to 7 cycle. If you have a homomorphism to 7 cycle, then you also have a three coloring because there is a homomorphism from here to here. Okay, so the promise is stronger than just having three coloring, but anyway, the promise doesn't help. This problem is still NP complete. So no non-trivial promise. This is a concrete example with 7 cycle. No non-trivial promise helps with three coloring. Okay, that's the real theorem here. And again, the math is still like yet different from the other two. This time it's algebraic topology. So again, this is not a CSP as I define it. It's a promise CSP. It's now a popular topic where you have two structures, one like the promise structure and then what you want to achieve. And again, the complexity depends on symmetries. This time symmetries would be homomorphisms from the nth power of the cycle of the first structure to the second structure, to the triangle. Okay, and again, we want to somehow show that it's close to dictator. So there are some important coordinates and the rest is not so important. The way how you do it here is that, well, if you look at this, it looks like a circle almost, and this as well, if you look at it from distance. Okay, so you can actually do it rigorously, assign to each of such homomorphism continuous mapping from the n-dimensional torus. Okay, circle to the n is a torus to the circle. So for n equal to 2, you have a mapping from a torus to a circle. And then you somehow play with winding numbers and such things. And where the function winds most, this is the important coordinate. Okay, so this is somehow this idea is started by Lovász, started topological combinatorics, it's called. So all this is like in this very simple objective, to analyze more than unary mappings, not just unary mappings as in group theory, but more than unary. It's a rich, mathematically rich, source of problems. And I guess that's all. So let me just wrap up. So 3 messages: triangle is not symmetric at all. Okay, only the obvious symmetries are there. Second, at least within CSP, but hopefully everywhere, complexity is determined by symmetry. And yeah, the third message: analysis of symmetries is fun. You can, like, whatever kind of math you like, you find it there. Right, so that's it. Thanks.
Thank you, Libor. Do we have any questions?
Yeah, could you just go over the idea of a clone again, please?
Sorry, I could not hear you. Can you repeat?
Could you just explain again what is a clone?
Yeah, okay, I didn't define it. So it would be family. Okay, let me try this. It would be a family of functions from nth power of a to a, so this will be clone on a, which is closed under forming any kind of term operations. Okay, so family of such mappings closed under, let's say, composition. Okay, so it's like analogous to say permutation group or transformation monoid. It's a family of unary mappings closed under composition and containing, say, identity. Okay, and here it is a family of not necessarily unary functions that is closed under any meaningful ways how to define new functions from old. So, for example, if a binary f and g is in a clone, I can define a ternary function by say f, g, yx, z. Okay, so this is a meaningful definition, or like defining a new function by a term in terms of the functions I have in the clone, and the condition is that this h would be in the clone as well. So it's a family of functions closed under forming term operations. Mm-hmm. In particular, it always contains projections. Okay, so the dictators, because this is also for meaningful definition. Is that
so? Is that part of the definition that it always contains the dictators?
Well, it follows from my definition. So, family of functions closed under forming term operations. This is a term operation, this h here, and so it always contains dictators.
Right. Okay. Thank you.
Do we have any more questions for Libor?
Sorry, does the n have to be fixed in this definition? Or?
No. N is not fixed.
Oh, okay. Thank you.
Finite, but not fixed.
Any further questions for Libor? Well, if not, then let's thank our speaker again. It was a really nice talk, and it was nice to see that symmetry can be also something else than a group, even though I might have some issues with that, but that's, I guess, a personal opinion. So thank you for the talk one more time.
Yeah, thank you for listening.
Yeah, thank you.